You've grown up thinking Saturn is gorgeous, peaceful, iconic. It's not. In this video, you're going to find out why the most beautiful planet in the solar system is also its most terrifying. But before we continue, please subscribe to the channel to give your support. Let's continue. How can a planet be big enough to hold 95 Earths in its mass, but still be light enough that it would float on water if you had an ocean large enough to hold it? Saturn's average density is about 0.69 grams per cubic centimeter, while liquid water is 1 gram per cubic centimeter, so Saturn is roughly 30% less dense than water. You are dealing with a planet that has a mass of about 5.68 times 10 to the 26 kilograms, around 95 times Earth's mass, spread out over a diameter of about 116,000 kilometers, around 72,000 miles. That tells you straight away, this is not a normal solid world. The reason is simple. Saturn is made mostly of hydrogen and helium. Those are light elements, and Saturn has collected a huge amount of them. Under Saturn's gravity, those gases are stacked in layers. The upper layers are cold, thin gas. Deeper down, the gas gets denser and hotter until it behaves more like a liquid. And even deeper, it becomes metallic hydrogen, where hydrogen atoms are squeezed so hard that their electrons move freely, like in a metal. So when you hear that Saturn would float, it is not a party trick fact. It is a clear sign that this planet is basically a giant, low-density ball of compressed gas and fluid, with extreme physics happening as you go down. That leads to the next question. Where exactly is the surface on a planet like this, and where could you stand or land? On Saturn, the honest answer is there is nowhere. There is no sharp boundary where the atmosphere ends and a solid ground begins. Instead, you have gas on top, then thicker, hotter gas, then supercritical fluids where gas and liquid are basically the same thing, then metallic hydrogen, and maybe, deep inside, a core that is not even a clean solid, but more like a dense, hot mixture of rock and ice. If you drop the probe through the cloud tops, it would not have a moment where it suddenly hits ground. It would just keep falling into regions where the pressure rises fast. At the level where the pressure is about 1 bar, similar to Earth's sea level, you see the visible clouds. Go 10 times deeper in pressure, then 100 times, then 1,000 times. Within a few thousand kilometers of descent, the pressure reaches hundreds to thousands of times Earth's surface pressure. Submarines that can handle the deepest trenches on Earth, a few dozen kilometers down in the ocean, would be crushed long before reaching those levels on Saturn. Even the strongest alloys we have, the metals that hold together rockets and deep-sea vessels, would eventually fold and collapse under that load. There is also the problem of temperature. As you go down, Saturn's atmosphere heats up. The combination of rising pressure and heat means that any probe you send in has a limited window before its structure, its electronics, its instruments all fail. So there is no landing on Saturn in the way we talk about landing on the Moon or Mars. There is only entry, descent, and then destruction. And once you accept that there is no stable ground, the next question is, what else about this planet is physically extreme? And how far does Saturn push basic rules like rotation and shape? Here's another fact you have to deal with. Saturn spins so fast that it is visibly squashed. One full rotation takes about 10.5 hours. That is a Saturn day. Because of this rapid rotation, Saturn's equator bulges outward. The equatorial radius is about 60,300 kilometers, while the polar radius, the distance from center to pole, is about 54,400 kilometers. That's a difference of almost 6,000 kilometers, or roughly 3,700 miles. On Saturn, that distortion is large and obvious. Gravity is trying to pull the planet into a sphere, rotation is trying to fling the equator outward, and what you see is the balance between those two effects. If Earth spun once every 10.5 hours, a point on the equator would be moving so fast that many tall buildings would need special design just to remain stable against the sideways pull. On Saturn, this extreme rotation is built into the planet's structure, and it affects everything from the winds in the atmosphere to the shape of the magnetic field. So you have a planet with no surface made mostly of gas, spinning fast enough to distort its own shape. Now add the timescale of its orbit. Saturn circles the sun at an average distance of about 1.4 billion kilometers, around 900 million miles, a bit more than 9 times farther out than Earth. At that distance, a year on Saturn, one full orbit around the sun, takes about 29 and a half Earth years. How does that stretch basic things like seasons and long-term change? On Earth, each season lasts a few months. On Saturn, each season lasts more than 7 years. If you defined a New Year's Day for Saturn, a child born on that date would be close to 30 years old before the next Saturn New Year. For missions and long-term operations in that system, changes in sunlight, ring shadows, and viewing angles play out over decades, not months. Time in the Saturn system does not move the way you are used to, and that slow cycle adds another layer of difficulty and risk. Put all this together and you see why Saturn feels wrong. It's a planet that would float on water, yet it can crush any known structure if you go down far enough. It spins so fast that it is physically distorted, yet it holds onto a layered atmosphere thousands of kilometers deep. It takes almost 30 Earth years to go around the sun once, stretching basic rhythms like seasons into something that barely lines up with a human life. For you and for your technology, this is not a friendly environment. Saturn is not just another gas giant. It's a low-density, ultra-fast spinning, no-surface, high-pressure system with a year as long as a human generation. This is the baseline, before you even talk about storms, rings, radiation, or moons. So the real unsettling question is this. If the basic structure of Saturn is already pushing gravity, rotation, and time this hard, what happens higher up in those banded clouds, where all that energy gets turned into winds and storms on a planetary scale? How do you get winds so fast they are brushing against the speed of sound on a planet that is already trying to crush and stretch everything around it? Saturn's equatorial winds can reach around 1,800 kilometers per hour, about 1,100 miles per hour. That is faster than a typical passenger jet cruises on Earth, and in Saturn's cold hydrogen atmosphere, it is not that far below the local speed of sound. On Earth, jet streams in the upper atmosphere move at maybe a couple hundred kilometers per hour, a few hundred miles per hour. On Saturn, the background wind in the equator belts is turned up to something closer to a continuous worldwide storm. Those winds are not just numbers, they set the baseline conditions for everything else happening in the atmosphere. You are dealing with a deep layer of hydrogen and helium heated from below by Saturn's own internal energy and twisted by a 10.5-hour rotation period. The planet is rotating so fast that any rising plume of gas gets pulled sideways, stretched into long bands that wrap around the whole planet. The result is a set of high-speed jet streams that barely flow down because there is no rough ground, no mountains, no forests, nothing solid at all to drag on them and bleed off their energy. So when you look at a picture of Saturn and you see those pale bands and streaks, you are not seeing gentle clouds. You are seeing the tops of wind systems that can sling a cloud the size of the city around the planet in a matter of hours. If this is the normal airflow on Saturn, the next question is, what happens when those conditions focus into a single organized storm, and that storm locks itself onto one place and refuses to die? At Saturn's North Pole, there's a hurricane-like structure that does exactly that. At the center of it, there's an eye about 2,000 kilometers wide, around 1,250 miles, roughly the size of a small continent. For comparison, the eye of a typical strong hurricane on Earth might be tens of kilometers wide, maybe a few dozen miles. This polar storm's eye is more than 20 times larger. The surrounding eye wall carries winds that make a Category 5 hurricane, the most intense class we have on Earth, look like a normal bad storm day. The unsettling part is not just the size or the speed, it's the time scale. On Earth, even the strongest cyclones last days to a few weeks before they lose strength, hit land, or get cut off from their warm water source. On Saturn, this polar vortex is effectively permanent on human timescales. We've seen it in data from the Voyager missions in the 1980s. We saw it again in detail with Cassini in the 2000s and 2010s, and it is still there. It sits over the pole, continuously fed by temperature differences and the planet's rapid rotation, and nothing ever breaks it up because there is no solid surface and no continents to interfere. You have a planet where one hurricane at the pole forever is just a starting condition. That leads to a bigger question. If a single storm can lock onto a pole for decades, what does it look like when the entire planet's atmosphere decides to erupt, not just in one spot, but across a whole latitude band at once? Every so often, roughly once per Saturn year or so, the planet produces events called great white spots. These are enormous storm systems that erupt in the mid-latitudes and then grow until they wrap around the entire globe. The bright clouds they produce can be seen from Earth-based telescopes as they expand and encircle the globe. These storms can last for months at the visible cloud tops, turning an entire hemisphere into a boiling bright disturbance. When the upper clouds finally fade, the story is not over. Radio and microwave observations show that the disturbance in temperature and composition can linger deep in the atmosphere for years, even decades. The storm leaves a kind of scar in the deeper layers, a leftover structure in the temperature profile and chemical makeup. On Earth, meteorologists track storms over days or weeks. On Saturn, a single global storm can appear, rage for months, then leave behind changes that last longer than some scientists' careers. This is where the climate horror feeling comes in. You're dealing with a system where weather and climate blur together. A storm is not a short event that comes and goes. It's something that can reorganize a chunk of the atmosphere for a large fraction of a Saturn year. And if these storms can reshape the planet's weather for so long, the next question is what is happening inside these clouds at the small scale, where collisions, ice, and electricity turn these already extreme systems into something even more dangerous. Inside Saturn's clouds, ammonia and water droplets move around in very cold hydrogen and helium. As these droplets collide, separate, and freeze or melt, they build up electric charges, just like storm clouds on Earth do, but under much more extreme conditions. The result is lightning that is so powerful, the Cassini spacecraft detected it as intense bursts of radio noise from thousands of kilometers away. Some of these flashes are estimated to be thousands of times more energetic than a typical lightning strike on Earth. For any probe trying to descend on a parachute through one of these storm systems, this is a lethal combination. You have winds faster than the fastest race cars ever built, turbulence that can tear structures apart, and electrical discharges that can punch through insulation, fry electronics, and vaporize parts of the craft. You're not just worried about heating and pressure, you're worried about being repeatedly hit by bolts that carry more energy than any lightning we've ever experienced directly. So when you stack up all these details, you have to ask, why are Saturn storms this extreme? Not just bigger versions of Earth storms, but qualitatively more dangerous. What is the underlying engine that makes them so powerful and so persistent? Saturn storms are running on more fuel and fewer brakes than the storms you know. First, the planet has a strong internal heat source. Saturn radiates more than twice as much energy as it receives from the sun, because it is still slowly contracting under its own gravity, and because processes like helium rain release extra heat inside. That heat drives convection, hot material rising, cooler material sinking through a very deep atmosphere. Second, Saturn's rapid rotation strengthens the Coriolis effect, the apparent force that bends moving air into spirals and bands. That means small disturbances can quickly organize into large rotating systems, and once they do, rotation helps hold them together. Third, there is no solid surface. On Earth, storms lose power when they move over land or colder water. Friction with mountains, forests, and rough terrain breaks them up. On Saturn, there is only thick gas and fluid underneath. A storm can dig deeper, connect to lower, hotter layers, and keep feeding on that energy. The result is an atmosphere where jet streams run at near sonic speeds. Polar vortices stay locked in place for decades. Planet-wrapping storms can leave long-lived scars, and lightning reaches energies we barely have words for. This is not just bad weather. It is a system where weather is one of the main ways the planet vents its internal stress. And yet, all of this still looks messy and chaotic. Bands and spots and swirls. The most unsettling thing sitting above Saturn's clouds is not chaotic at all. It is a storm that decided to organize into a clean, six-sided shape and then stay that way for decades. So the next question is, what does it mean when a gas giant with all this turbulence draws a perfect hexagon on its own pole and refuses to erase it? How do you get a storm with straight edges on a round planet and keep it locked in place for decades without it falling apart? Near Saturn's North Pole, around 78 degrees north latitude, there is an atmospheric feature that does exactly that. From space, it looks like a clean, six-sided shape wrapped around the pole, a hexagon roughly 30,000 kilometers across, about 18,600 miles. That is wide enough to fit two Earths side by side. Each side of this pattern is about 14,500 kilometers long, around 9,000 miles. This is not a continent or a rigid structure. This is moving gas, forming a precise geometric outline on a planet that is otherwise full of bands, swirls, and chaotic storms. This is not how we normally expect nature to behave at this scale. Fluids on planets like to form circles, spirals, blobs, and irregular shapes. On Earth, jet streams meander, hurricanes form spirals, and even when patterns repeat, they do not snap into perfect polygons. So when you see a storm system the size of a gas giant's polar cap drawing straight edges and sharp corners, it stands out immediately. It is a sign that Saturn's atmosphere is following rules that only show up when you have a deep layer of gas, a huge planet, and a rotation rate as fast as Saturn's. Underneath that shape, the basic physics is straightforward. The hexagon is a jet stream, a high-speed river of gas flowing around the planet with winds of around 320 kilometers per hour, about 200 miles per hour. That speed is not extreme compared to Saturn's fastest equatorial winds, but what matters here is how organized the flow is. The jet stream runs around the pole, and instead of forming a smooth circle, it breaks into a standing wave pattern, a repeating up and down in latitude that adds up to 6 big bends. Those bends line up in a way that creates the 6 sides of the hexagon. The jet stream moves around the pole with a period that matches Saturn's deep internal rotation rate, not just the motion of the upper clouds. That detail is important because it means this feature is not just a shallow weather pattern floating on top, it is tied to the rotation of the planet as a whole. Think of a racetrack wrapped around the top of a world, with traffic moving at about 320 kilometers per hour. Now, instead of a circular track, the path itself has 6 broad corners, and the traffic keeps that exact track shape lap after lap, year after year. The gas is constantly moving, molecules are streaming past each other, but the overall pattern, the hexagon, holds its form. The really uncomfortable part is how long this has been going on. The hexagon was first clearly seen in images from the Voyager spacecraft in the early 1980s. When the Cassini spacecraft arrived at Saturn in the 2000s and sent back high-resolution images and movies, the hexagon was still there, in the same place with the same basic shape. More recent observations from Earth-based telescopes show it has persisted for at least 40 years of our observations, and it is probably much older than that. For a chaotic, turbulent gas on a fast-spinning planet, 40 years of stability is enormous. On Earth, jet streams wobble from week to week, storm tracks shift every season. Even features like the polar vortex over Antarctica change shape and strength year after year. Saturn's hexagon, by contrast, behaves more like a long-term part of the planet's climate system, a structure that survives shorter-term chaos around it without being erased. That tells you there is some deep, stable configuration underneath, some balance between rotation, temperature gradients, and jet speed that locks this pattern in place. You might think once scientists recreated this effect in the lab, it would stop feeling strange, but the lab work actually makes it more unsettling. Researchers built rotating tanks filled with fluid, spun them, and set the inner fluid rotating at a different speed than the outer ring to mimic how winds can shear in a planetary atmosphere. When they tuned the speeds just right, they saw polygonal patterns appear at the boundary between the different flow speeds, sometimes triangles, sometimes squares, but one of the most common and stable shapes that appeared was a six-sided pattern, a hexagon. Those experiments show that you can get long-lived polygons in rotating fluids using only basic physics, no solid barriers, no hidden machinery. But that doesn't really make Saturn's hexagon ordinary. Instead, it says that under the right conditions, rotating fluids naturally want to snap into these geometric patterns, and they can hold them for a long time. On a lab table, that pattern might be a few centimeters across. On Saturn, the same underlying physics is acting on hydrogen and helium, and the pattern stretches 30,000 kilometers. So this turns Saturn's North Pole into more than just a patch of bad weather. It's a natural fluid dynamics experiment that runs at a planetary scale, all the time powered only by Saturn's rotation, gravity, and internal heat. There is no engineer maintaining it, no control system adjusting it. The atmosphere, left alone, organizes itself into a design that people often describe as artificial looking, even though it's not. Saturn shows that physics, by itself, can assemble structures that look planned, and it can keep them running longer than a human career. Put this next to what you already know about Saturn: the low density, the crushing depths, the rapid rotation, the huge storms, and the picture gets sharper. This is not just a planet with extreme weather. It's a system that can spontaneously generate and maintain clean geometric structures out of chaos, using nothing more than gas and motion. If Saturn can do this at one pole with one jet stream, it forces you to ask a harder question: what other large-scale structures can form in that deep, fast atmosphere, and how many of them would push past your idea of what a normal planet should look like? And if Saturn can quietly run a hexagon for decades on top of everything else it's doing, what happens when you move your attention out from the pole and into the bright, thin structure that wraps all the way around the planet, the place where gravity and tidal forces go to work on ice and rock and turn moons into debris? How do you get something that is almost 290,000 kilometers wide, but only a few tens of meters thick, and still act like a weapon zone around the planet? Saturn's main rings stretch out to about 282,000 kilometers from the planet's center, roughly 175,000 miles. But most of that bright ring material is only around 10 to 30 meters thick, about 30 to 100 feet. Scaled down, if you shrank the rings so their width matched the distance between two big cities, say 1,000 kilometers or about 600 miles, their thickness would be like a sheet of paper. You're looking at one of the flattest, thinnest large structures in the solar system, a blade of ice and rock that wraps all the way around Saturn. From a distance, it looks clean and smooth. Up close, it's anything but. So the real issue is, what are those extremely thin, extremely wide rings actually made of? And how dangerous are they if you try to fly through them? The bright main rings form a disk with a diameter of around 270,000 kilometers, about 170,000 miles. That is nearly 3/4 of the distance from Earth to the Moon. But the total mass in that disk is surprisingly low, about 1.5 times 10 to the 19 kilograms, or roughly 15 billion kilograms. That is only around 40% of the mass of Saturn's small moon, Mimas. So you have a structure that looks massive, but in total weight, it is less than half a tiny moon. For a spacecraft, though, the total mass is not what kills you. The problem is how that mass is distributed. The rings are made of countless separate pieces, from dust grains to pebbles to chunks the size of cars and houses, tens of meters across. Each piece orbits Saturn at high speed, several kilometers per second, thousands of meters per second. For you, trying to send a probe or a crewed ship through that disk, it is like flying through an endless three-dimensional minefield of ice bullets. Even a tiny grain can punch a hole if you hit it at orbital speed. A boulder-sized chunk is simply fatal. So when people talk about threading the rings, they're talking about navigating a region where everything is moving fast, everything is solid, and your safe paths are narrow gaps that you have to hit with extreme precision. The rings look delicate and light from far away. Locally, they are a dense traffic zone of debris on intersecting orbits. That leads to the deeper question. Why does Saturn even have this strange, thin disk of icy wreckage in the first place? And what had to happen to put it there? The composition gives you a big clue. The rings are more than 99% pure water ice, with only a small amount of darker dust and rock mixed in. That already tells you you're not looking at leftover gas from planet formation. You're looking at processed material, something that has been sorted and refined. Their structure, with gaps, waves, and clumps, hints at a violent history and ongoing gravitational interactions with Saturn's moons. Recent models suggest a scenario where an icy moon, sometimes nicknamed chrysalis, got destabilized. Over time, its orbit shifted until it came too close to Saturn. Once it crossed the critical distance, Saturn's tidal forces tore it apart. Its rockier core may have plunged into the planet, while its outer icy layers were shredded and spread out into a disk. Over a few 100 million years, collisions between fragments ground the debris down into the thin ring system we see today. When you study the rings now, you're doing something like forensic astronomy, reading the remains of a destroyed world. You're literally orbiting a crime scene where gravity ripped the move apart and left its pieces stretched into a razor-thin band. This is where the Roche limit comes in, the basic rule that decides whether something stays whole or gets shredded. The idea is simple. If an object, like a moon, gets close enough to a massive planet, the difference in gravity between its near side and its far side becomes strong enough to overcome the object's own self-gravity. The near side is pulled harder than the far side. The moon can no longer hold itself together, and it breaks into pieces. To make that intuitive, think of standing on top of a very tall ice cliff near Saturn. The planet's gravity pulls on your feet slightly harder than on your head. On Earth, that difference is tiny. You never feel it. Near a massive planet like Saturn and at short distance, that difference grows. Scale yourself up to the size of a small moon, and now feet versus head becomes near hemisphere versus far hemisphere. If the tidal pool becomes stronger than the moon's own gravity, the structure fails. You do not get craters, you get fragments stretched out along the orbit, which then collide and grind down into rings. That same physics is still active today. Any object that wanders inside Saturn's Roche limit and stays there will be at risk of being pulled apart. The rings you see are a snapshot of that process, a zone where gravity is actively grinding material down instead of letting it clump up into a stable moon. But there is another twist. The rings are not a permanent fixture. They're slowly disappearing. Observations show that the rings are losing material in a process often called ring rain. Tiny charged ice particles get influenced by Saturn's magnetic field and spiral down along magnetic field lines into the upper atmosphere. The rate is hundreds to thousands of kilograms per second. Over tens of millions of years, that adds up. Estimates suggest that the rings could vanish or at least fade dramatically in less than 100 million years. On cosmic timescales, that's not very long. So you're living in a rare window of time when Saturn has a bright, massive-looking ring system. Billions of years ago, it might not have had these rings at all. Billions of years in the future, they may be gone, turned into a thin haze in the upper atmosphere, or fully absorbed into the planet. Right now, though, Saturn is wearing a lethal debris disk that both shows you how it tears moons apart and how it slowly eats the leftovers. From far away, the rings make Saturn look beautiful and calm. Up close, they're a thin, wide execution zone, created by tidal destruction, maintained by constant collisions, and doomed by ring rain. They're the most visible proof that in Saturn's neighborhood, gravity doesn't just hold things in orbit, it also grinds them down. And that raises the next problem. If Saturn can tear apart moons and drag their remains into its atmosphere, what is it doing to the space around it? The invisible region where magnetic fields and charged particles form a different kind of trap, one that you can't see but that can kill hardware and humans just as effectively. How do you explore a planet when the space around it is already dangerous before you even touch the atmosphere or the rings? Around Saturn, the first thing you run into isn't rock or ice, it's a magnetic bubble, the magnetosphere, carved out of the solar wind. On the day side, that bubble extends to roughly 20 Saturn radii from the planet, and on the night side, it stretches into a long magneto-tail that runs for hundreds of Saturn radii downstream. In real numbers, you're talking about a structure tens of millions of kilometers across. Inside that bubble, charged particles are trapped and guided by Saturn's magnetic field. A lot of that plasma isn't coming from the sun, it's coming from inside the system, especially Enceladus, the icy moon that spits water vapor and ice into space. Those particles get broken apart into oxygen-rich ions and other charged fragments, and the magnetic field takes them for a ride. So instead of empty space, you have a huge invisible environment of moving particles and fields, and anything you send in has to survive that first. Here's the part that sounds backwards at first. Saturn's magnetic field at the surface is actually weaker than Earth's, but its total magnetic strength, its magnetic moment, is 580 times Earth's. The field fills such a huge volume that the overall magnetosphere is enormous. For you, that means that even if the local field at some point feels weaker than what your compass sees on Earth, the effects add up over large distances and long times. Space near Saturn is not just vacuum and sunlight. It's an electromagnetic environment that can charge up your spacecraft, fry unprotected electronics, and slowly dose astronauts with radiation. Particles spiraling along magnetic field lines can hit hardware again and again, and high-energy electrons and ions can penetrate shielding if you don't design it properly. The risk is not just a single big burst, it's also the constant background, the slow, grinding dose that accumulates over weeks and months in orbit. Now, connect this to the rings. The same magnetic field that traps charged particles is also interacting with the ring material. Tiny ice grains in the rings can pick up electric charge from sunlight and plasma. Once charged, they feel not just gravity, but the magnetic field too. Some of them get pulled off their orbits and slide down the magnetic field lines into Saturn's upper atmosphere. This ring rain moves hundreds to thousands of kilograms per second. When that icy material hits the upper atmosphere, it alters the ionosphere, the layer of charged gas near the top. It changes how easily radio waves travel, it changes the local chemistry, and it feeds processes that light up Saturn's poles with auroras. Those auroral ovals shine brightly in ultraviolet, pumping out power on the order of half a terawatt, hundreds of billions of watts, as charged particles crash into the atmosphere and excite atoms and molecules. For a human crew looking at that, the auroras are not just pretty light shows, they are glowing warnings that you are in a region where high-energy particles are active. That is the context in which Cassini flew its final orbits. During the last phase of its mission, it dove repeatedly through the gap between the innermost rings and the planet itself, sampling the plasma, dust, and magnetic field in that region. Those orbits took the spacecraft through zones where the environment was not fully predictable, with rapidly changing particle densities and field strengths. Cassini measured ring rain directly. It tasted the atmosphere, and it helped pin down the strength and structure of Saturn's magnetic field. But notice how the mission ended. We did not try to land Cassini on a moon. We did not park it in a safe graveyard orbit. NASA deliberately sent it down into Saturn's atmosphere, where it burned up. The reason was not that we could not think of anything else to do with it. The reason was that Saturn's system includes moons like Enceladus and Titan, which may have environments where life could exist. If Cassini crashed into one of those moons by accident, microbes from Earth that survived on the spacecraft could contaminate those habitats. So the safest option, both scientifically and ethically, was to use Saturn's own hostility as a disposal tool. By sending Cassini into the atmosphere, the heat and pressure ripped the spacecraft apart and sterilized it. We ended a successful mission by literally feeding it to the planet, because the entire system is so sensitive and so dynamic that you cannot trust a dead spacecraft just drifting forever. When you add all this up, Saturn's magnetosphere is not just background physics. For humans and hardware, it is an invisible, shifting minefield. It can charge up surfaces until they arc. It can slowly damage electronics. It can force you to use heavy shielding. And it directly powers other threats like ring erosion and intense auroras. It may also be driving complex chemistry in the upper atmosphere and in the environments around the moons, reactions we do not fully understand yet. To move around Saturn, to study its rings and moons, you have to move through this electromagnetic engine, a planetary-scale system of fields and plasma that does not care if you're there or not. It is the first layer of danger wrapped around the planet that already wants to crush, cook, and tear apart anything that gets too close. So then the next hard question is this. If the space around Saturn is that hostile, what actually happens when you stop orbiting and start falling? When you drop into the atmosphere itself and turn all that speed into heat, shock, and pressure during the longest, worst skydive you could possibly take in the solar system? How fast do you hit the air when the planet below you has almost no surface and the gravity well that deep? A probe dropping from orbit around Saturn can slam into the upper atmosphere at tens of kilometers per second. Even if you design a relatively gentle trajectory and come in at about 20 kilometers per second, around 45,000 miles per hour, that is still way beyond the speed of a rifle bullet and getting close to the speed small meteoroids have when they hit Earth. At those velocities, the kinetic energy in every kilogram of the probe is huge. You can think of each kilogram as carrying energy on the same order as a kilogram of high explosive, and all of that energy has to go somewhere, very fast. As the probe hits the first thin gas at the top of Saturn's atmosphere, it starts ramming into hydrogen and helium atoms at extreme speed. The air cannot get out of the way, so it compresses and heats up, forming a super hot plasma layer in front of the heat shield. That thin metal and ceramic has to absorb and deflect a huge power flow, megawatts per square meter, for as long as the entry lasts. If anything about the shape is wrong, if the shield has a flaw, if the probe tumbles, the heating can jump up in one area and punch straight through. On Earth and Mars, we have tested heat shields and have some experience. On Saturn, we have no tested designs for a direct, deep entry probe, so the first one would be flying into a regime where a small miscalculation in speed or angle means total failure in seconds. Now add the second problem. You're not just dealing with heat, you're dealing with pressure that ramps up and never lets you stabilize. On Earth, you can say surface pressure is 1 bar, and most of our hardware is designed to deal with that, or maybe a few times that. On Saturn, 1 bar is just a start. It marks the level of the visible cloud tops, the point in the atmosphere where the pressure equals Earth's sea level. Drop down to 10 bars, you're already in an environment harsher than the deepest parts of Earth's oceans. Go to 100 bars, 1,000 bars, and within just a couple of thousand kilometers of vertical fall, the pressure climbs into the range of hundreds to thousands of times Earth's surface pressure. At those levels, the gas behaves as a supercritical fluid. Not really a gas, not really a liquid, just a very dense, hot medium. Most materials are completely out of their design envelope here. Metals deform under their own weight, seals and joints flow, electronics fail. Our strongest deep-sea submersibles are built for maybe 1,000 bar, in special cases a bit more. Saturn's interior can push far past that, and there's no solid hole you can hide inside that will hold indefinitely. Eventually, every structure you send in reaches a depth where it starts to crumple, and then, very quickly, it loses integrity completely. There is no point where you break through into a stable layer and rest. There is only more pressure. Pressure is not acting alone. As you fall, temperature keeps rising as well. Saturn's interior is not cold, it's a heat well. Models suggest that near the core, the temperature may reach around 11,700 degrees Celsius, hotter than the visible surface of the sun, which is around 5,500 degrees Celsius. You're moving from a region where hydrogen is a cold gas, through layers where it's a warm gas, then a hot, dense fluid, then a metallic state, where electrons are free to move. Helium, the second major component, stops mixing smoothly with hydrogen at certain pressures and temperatures. It can separate and condense into droplets, falling inward as helium rain. That rain releases extra heat as it drops deeper into the gravitational field. The chemistry of matter itself changes with depth. Materials you designed on Earth, steel, ceramics, composites, are not meant for these combinations of pressure and temperature. They lose stiffness, conductivity changes, chemical bonds fail in ways you cannot test easily on the ground. The key point is, you never hit a solid core like an asteroid hits the ground. You don't get a single violent impact and then rest. Instead, you keep entering new regimes of physics where the rules for how matter behaves shift, and every step down is harsher on your structure than the last. You're moving toward a region that behaves more like the interior of a failed star than any planet you know. Cassini's final plunge gave us the first real taste of what even the upper part of that journey looks like. During its last orbit, the spacecraft skimmed into Saturn's upper atmosphere. As it hit denser gas, its radio link back to Earth started to show the effects of drag and heating. Instruments measured changing densities, traced out the composition, and felt the beginning of the aerodynamic forces that were about to destroy the craft. Very quickly, the combination of heating, drag, and structural stress overwhelmed Cassini. It was not built as an entry probe, so this was expected. But the key thing is, all our direct data stops in the thin upper layer. Below that, we only have models and indirect measurements. We have never put a sensor into the deep regions at hundreds or thousands of bars. We have never exposed real materials to Saturn's exact mix of pressure, temperature, and composition at those depths at full scale. Every kilometer you go below where Cassini died would be a step into a physical regime we have never tested in a lab at that size and duration. For a human, the story is even shorter. You cannot survive the heating at entry speed without being inside a heavily shielded capsule. You cannot survive the pressure ramp without a structure orders of magnitude stronger than anything we have flown. You cannot survive the temperatures as you go deeper because no life support system can operate when the surrounding environment is hot enough to melt metals. Even in a thought experiment where engineering is far beyond what we have now, you end up with a vehicle that, at some depth, has to fail. There is also the psychological side, which is simple and brutal. On Saturn, there is no bottom to hit in any useful sense. You do not land, you do not touch ground and step out. You fall, you are slowed a bit by drag, then you accelerate again as you get denser and heavier, then you are crushed, burned, or dissolved into the planet. Saturn is like an endless vertical ocean with no seafloor that you can ever reach, only layers that get more hostile the lower you go. If falling straight in ends with you being erased without ever standing anywhere, what happens to objects that do not fall directly down but hover in dangerous orbits instead, getting tugged and stretched by gravity until they break? How does Saturn reshape the things that stray too close, not just by crushing them, but by pulling them apart and grinding them into rings and rubble around the planet? Why do some worlds hit Saturn, get torn apart and smeared into a ring, while others stay whole and keep orbiting? The difference comes down to one simple idea, the Roche limit. If a moon or any large object comes in sight a certain distance from Saturn, the difference in gravity between its near side and far side becomes stronger than its own gravity holding it together. At that point, you do not get craters from impacts, you get confetti. The whole object is pulled apart by tides. Think of the forces acting on a moon. Its self-gravity is trying to pull all its material toward its center, keeping it as a single body. Saturn's gravity is pulling harder on the side facing the planet and a bit less on the far side. That difference is the tidal force. Far from Saturn, the moon's own gravity wins easily. It stays intact. As it moves inward, Saturn's gravity gets stronger and the tidal difference grows. Once the tidal force across the moon becomes larger than the moon's self-gravity, the structure cannot hold. Rock, ice, everything starts to pull apart along lines of weakness. Instead of one solid sphere, you get a stream of fragments spread along the orbit. That boundary distance, where tides beat self-gravity, is the Roche limit. Inside that limit, no loosely held body can survive for long as a single solid object. A rubble pile asteroid, a weak icy moon, anything like that will slowly stretch, crack, and finally break into pieces. Outside the Roche limit, solid moons can exist and even be reshaped, but not totally shredded. That one invisible boundary line decides whether Saturn makes a world or destroys it. So once you know that, the next question is, what does Saturn actually do with the material that crosses that line and gets torn apart? The answer is in the rings. Current models say Saturn's bright main rings are not ancient leftovers from the birth of the solar system. Instead, they likely formed within the last 100 million years or so, which is recent on a 4.5 billion year timeline. The leading idea is that one or more icy moons drifted inward, hit the Roche limit, and got destroyed by tidal forces. Their rocky cores may have fallen into Saturn, while their ice-rich outer layers were ripped off and spread out into a disk. From there, collisions between fragments grind the debris down. Some pieces clump briefly, then get pulled apart again. Resonances with nearby moons stir the material, carve gaps, and maintain structure. What you see today as a smooth, bright ring is actually the active disintegration zone, where Saturn is still processing the remains of those moons. It's not a gentle halo. It's a place where anything that wanders too close is broken and slowly turned into smaller and smaller particles. That's why thinking of the rings as peaceful arcs is misleading. Saturn is running an ongoing execution zone around itself, and the rings are the evidence. But tidal forces do not only destroy. At slightly larger distances where the moon's self-gravity still wins, tides act in a different way. Saturn's gravity flexes its moons as they orbit, especially ones like Enceladus that are locked in orbital resonances. As the moon moves closer and farther in its slightly stretched orbit, Saturn's pole stretches and relaxes its interior again and again. That repeated flexing turns orbital energy into heat through friction inside the rock and ice. On Enceladus, that tidal heating is strong enough to keep a subsurface ocean of liquid water from freezing solid, even though the surface is at around minus 180 degrees Celsius, or roughly minus 290 degrees Fahrenheit. It drives geysers at the South Pole, where water vapor and ice grains erupt through cracks and vent into space. The same process at different levels shapes other moons, creating cracked surfaces, smooth plains, and possible internal oceans. So the very force that tears moons apart inside the Roche limit is, at safer distances, kneading them like dough and running geology and maybe even habitability. That leads straight to you and your hardware. If tides can tear a moon apart, what can they do to something small and engineered, like a spacecraft? A spacecraft is held together not by self-gravity, but by bolts, welds, and internal structure. When it flies through a strong gravitational gradient near Saturn, the part closer to the planet will feel a slightly stronger pull than the part farther away. For a small satellite far away, that difference is tiny, basically unnoticeable. But scale up the craft and bring it close enough, and you can measure real stress. Take something about the size of the International Space Station, around 100 meters long, and bring it deep into Saturn's gravity well. The gravitational pull on one end will be measurably different from the pull on the other end. The whole structure is under tension just from the planet's gravity trying to stretch it along its length. It's like a giant hand grabbing both ends and pulling, trying to turn it into a long chain of parts instead of one rigid object. You would have to design for that, just like you design for thrust loads or launch vibration. This tidal stress stacks on top of everything else: orbital mechanics, maneuvers, thermal swings, radiation. Get too close and you enter a zone where the planet is literally trying to pull your vehicle apart at the seams. That may not tear a spacecraft into pieces the way it does a moon, but it eats into your safety margins and forces you to stay farther out or accept higher risk. Put all of this together and Saturn's gravity stops looking like a simple force pulling things into orbit. It becomes a full system. It grinds large bodies into ring systems inside the Roche limit. It kneads moons farther out, heating them and driving cryovolcanoes and oceans. It stretches spacecraft that venture nearby, and any debris that slips inward eventually gets shredded, added to the rings, and then slowly drained down into the atmosphere as ring rain. Whole moons become rings. Rings become infalling particles. Those particles change Saturn's upper atmosphere over time. The planet's gravity is not just holding a stable family of moons, it is running a slow, continuous cycle of building, deforming, breaking, and consuming. It is a kind of cosmic blender operating on ice, rock, and metal over tens of millions of years. And while all of this is happening in the solid parts of the system, Saturn is also hosting worlds that, on the surface, look closer to Earth's scale, with atmospheres and liquids and weather, but built out of completely different chemistry. So the next question is, what does a shoreline look like when the ocean is liquid methane? The rocks are water ice and the sky is orange, all deep inside Saturn's gravity well. How do you get a tiny moon with air that feels heavier on your shoulders than Earth's? Titan's surface pressure is about 1.5 bar. Earth's sea level pressure is 1 bar. So when you stand at Titan's surface, the air pressing on you is about 50% higher than what you feel at the beach on Earth. The atmosphere is mostly nitrogen, just like Earth's, but loaded with methane and other hydrocarbons. Titan itself is only about 5,150 kilometers across, roughly 3,200 miles. That is smaller than Earth's diameter by a factor of around 2.5. Yet this small world carries a thick, deep atmosphere. Because the air is dense and the gravity is low, around 14% of Earth's gravity, about 0.14 g, flight behaves very differently. With a basic pressure suit, a human strapped to simple wings could, in theory, fly by flapping or using small motors. Your weight is low, the air is thick, lift comes easy. That sounds friendly at first, but look at what that atmosphere is made of and what it sits on. This is not a warm nitrogen-oxygen mix over liquid water. It is cold nitrogen mixed with methane and loaded with a haze of complex organic particles hanging over a surface that is hundreds of degrees below freezing. So the next question is, if the air is that thick and that cold, what is actually filling Titan's lakes and seas? What does an ocean look like on a world where water is not a liquid at all? On Titan, the average surface temperature is around minus 179 degrees Celsius, roughly minus 290 degrees Fahrenheit. At those temperatures, water behaved like rock. The solids that make up the ground are mostly water ice and frozen organics, rigid as stone. The liquids in Titan's lakes and seas are not water, they are hydrocarbons, mainly methane and ethane spread across basins hundreds of kilometers wide, tens to hundreds of miles across. When you stand near one of these seas, you're not looking at familiar salt water, you are looking at ultra-cold liquid methane and ethane, substances we treat as flammable gases and fuels on Earth. If you fell in without protection, you would not swim, you would sink and drown in a cryogenic hydrocarbon mix. Your lungs, your equipment, everything is designed for water-based environments. And here, the ocean is closer to rocket propellant than to anything you know from Earth. The density, temperature, and chemistry are all wrong for unprotected life. That immediately raises the next issue. What kind of weather system runs over liquids like that? And how far does Titan go in copying Earth's climate while swapping water for methane? How do storms work when the rain is methane and the rivers are carving through ice that behaves like rock? Titan has a full methane cycle, parallel to Earth's water cycle. Methane evaporates from the lakes and seas, forms clouds, moves with winds, condenses, and falls back as rain. Over time, that rain collects into streams, rivers, and channels that flow back into larger basins. Radar mapping from orbit has shown clear river channels, branching networks, and delta structures where flows spread out and deposit material, exactly the way rivers do on Earth. But they are cutting into a surface made of water ice as hard as stone at those temperatures. This means Titan is running an active climate engine, with storms, winds, and erosion, but the working fluid is a flammable cryogenic liquid. Storms don't just darken the sky, they move methane around, redistribute energy, and change the landscape. The soil is frozen hydrocarbons and ice. The rain is methane. Over long timescales, that reshapes the surface just like water does here, but every part of the chemistry is different. You're looking at something that feels familiar in shape, but not in substance. Once you see a full methane cycle operating like this, the next logical question is, in a place with thick air, steady energy input, and lots of complex molecules, does Titan have any chance of hosting its own version of life, however slow or strange? What does habitable mean when the world is this cold and this toxic to you? Titan's thick atmosphere provides shielding from radiation and a steady environment. The moon gets energy from the distant sun and from charged particles driven in by Saturn's magnetosphere. Photochemical reactions in the upper atmosphere build long, complex organic molecules, which then drift down as haze and settle on the surface. You have nitrogen, methane, and a continuous supply of more complex carbon-based compounds. On paper, those are important ingredients for interesting chemistry. But at minus 179 degrees Celsius, everything happens extremely slowly. Chemical reactions that would proceed in seconds or minutes in liquid water might take years or longer in these conditions. If something like life exists here, it would not be fast, active biology like you know on Earth. It would be slow, alien chemistry, maybe using liquid methane as a solvent instead of water, following rules we barely understand. For humans, Titan is a strange paradox. The combination of low gravity and dense air means that if you fell from a height in a proper suit, the thick atmosphere could slow you enough that you might survive the impact. You could walk, maybe even fly with assistance. But the place you land on is a frozen hydrocarbon landscape, with lakes of bitterly cold methane and ethane, and possibly a buried subsurface ocean of water under an ice shell. You survive the fall, but you land in a world where breathing, eating, and staying warm are all direct fights against the environment. So what is Titan really telling you about Saturn's system? From a distance, Titan looks Earthish. It has an atmosphere, clouds, and lakes. Up close, every detail is wrong for human life, and every detail is a warning that familiar shapes don't guarantee familiar conditions. The climate is active, but it's not running on water. The air is thick, but you can't breathe it. The seas are extensive, but they are filled with flammable cryogenic liquids. All of this is happening deep in Saturn's gravity well, under the influence of its tides and magnetosphere. Titan is like a training ground for the idea that a world can be geologically active and maybe chemically interesting for life while being completely hostile to you. It forces you to widen your definition of Earth-like beyond visuals and into chemistry and temperature. And while Titan shows you how far a big moon can push that idea with a thick atmosphere and seas, Saturn has another moon that takes a different route, much smaller, less dramatic from far away, but hiding an ocean that is directly venting into space. So the next question is, if Titan is the world where the oceans stay mostly hidden under haze, what do you get when a tiny moon like Enceladus blows its oceans streamed out through cracks at the South Pole? How does a moon only about 500 kilometers across end up holding one of the most important oceans in the solar system? Enceladus is tiny, roughly 310 miles across, but when Cassini flew past its south pole, it saw jets blasting straight out into space. These plumes reach hundreds of kilometers above the surface and are made of water vapor, tiny ice grains, and organic molecules. They're not just thin mist either. They are powerful enough that some of the material escapes and helps feed Saturn's E-ring. The source is not surface ice melting in sunlight. The material is coming from below, from a subsurface ocean that lies under an ice shell. The water is vented through long, warm fractures near the South Pole, called tiger stripes because of how they look in infrared and in imaging. Between those fractures, the region is hotter than you would expect for a frozen moon that far from the sun. That is your first clue that Enceladus is not just a frozen snowball, it is an active world with internal energy and liquid water. So once you know water is there, the next question is, does this ocean have the other ingredients you need for something like habitability? What would it take to call a place potentially habitable, even if you never see a single organism? When Cassini flew through the plumes and sampled the ice grains, the data showed more than just water. It picked up salts like sodium compounds and simple organic molecules, things built from carbon and hydrogen, sometimes with oxygen and nitrogen mixed in. The presence of salts tells you that the water has been in contact with rock, not just sitting isolated under ice. That is what you would expect if there are hydrothermal vents at the seafloor, hot water circulating through rock, dissolving minerals, and coming back into the ocean. For habitability, that combination matters a lot. You have liquid water as a solvent, you have energy in the form of heat and chemical gradients at those vents, you have chemistry with minerals and organics mixing. On Earth, deep-sea hydrothermal vents support rich ecosystems, even without sunlight, using chemistry as the energy source. Enceladus is not Earth, and this does not prove life exists there, but it checks the basic boxes: water, energy, and complex molecules. And all of that is happening on a tiny moon parked in a system that, overall, is incredibly hostile. So the twist is clear. You might have a cradle for life inside a radiation-blasted, gravity-dominated death trap. That is where the ethical problem starts for any future mission. How do you explore a place that might have its own biology without accidentally wiping it out with your own microbes? Every spacecraft we send carries some number of Earth organisms, even after cleaning. If you land something on Enceladus and that lander eventually breaks down and leaks, those microbes could get into the ice and, over time, reach the ocean. If Earth life can survive and adapt, it might outcompete or overwrite any native ecosystem before we even knew it was there. So any mission that goes near Enceladus has to be sterilized to a level beyond what we normally do. You need strict planetary protection, careful assembly in clean rooms, heat sterilization or other strong methods, and very conservative choices about where you land and what you do with the hardware once the mission ends. The horror here is not just physical. Saturn does not only threaten you with storms, rings, and gravity, it confronts you with the idea that you could destroy an alien biosphere with one bad decision. The fear is not, can we survive there? It is, can we visit without becoming the threat? The good news, scientifically, is that Enceladus offers a way to study its ocean without drilling through kilometers of ice. The plumes themselves are samples of that ocean, sprayed into space. If you fly a spacecraft through them at a few kilometers per second, you can scoop up ice grains and vapor and run them through instruments, mass spectrometers, dust analyzers, maybe even devices tuned to detect specific patterns in complex molecules. You do not have to land, you just have to fly the right path with the right shielding and sensors. The stakes are huge. A single spectrum from those collected grains could show not just basic organics, but more complex ones like amino acids or particular ratios of isotopes that hint at biological processes. You could get a fingerprint of ocean chemistry, maybe even a hint of life, without ever touching the surface. The catch is that you still have to operate in Saturn's magnetosphere, in its gravity field, and in a region full of tiny particles moving at high speed. The mission profile is risky and the science return is enormous, which is why Enceladus stays near the top of every list for future exploration targets. All of this leads to a bigger, uncomfortable pattern. Saturn's system hides its most promising habitable pockets in places that are not protected at all. Enceladus's ocean is covered by ice, but the plumes spray it directly into space, exposed to radiation, vacuum, and contamination risk. Titan's thick air shields its surface, but the chemistry there is so alien that anything we send is both a probe and a potential pollutant. These are not cozy, sealed biospheres. They're fragile niches sitting in a minefield of radiation, tidal forces, and human interference. So Saturn is not just a system of physical hazards. It's also a test of whether we can handle the responsibility of exploring places that might have life without breaking what we're trying to understand. And that leads directly into the next layer of threat, because even before you worry about oceans and microbes, you have to deal with the basic environment far from the sun, where light is weak, temperatures are brutal, and darkness turns every other danger up a notch. So the next question is, what does day and night really mean in a place where sunlight is only a faint glow and shadows can be as dangerous as any storm? How bright is day when you're 9.5 times farther from the sun than Earth is? At Saturn's distance, about 9.5 astronomical units, the sunlight is spread over a much larger area. The intensity drops to roughly 1/90th of what you get at Earth. So even when the sun is high in the sky, noon at Saturn is more like a deep, permanent twilight on a cloudy winter day on Earth. The sun is a small, sharp star, not a blazing disk. For you and your equipment, that low light level sets the tone for everything. Cameras need longer exposures, solar panels get much less power, and your eyes would never see anything close to a bright blue sky. The whole system lives in a dim, cold version of daylight. That sounds calm, but it's a constant reminder that you're right at the edge of where the sun still has much influence. And if the light is that weak, the next question is, what does that do to temperatures, and how does that affect chemistry and hardware? Look at the typical temperatures near Saturn's cloud tops. They sit somewhere between about -189 to -139 degrees Celsius, which is about -308 to -218 degrees Fahrenheit. At those temperatures, many gases you're used to on Earth would freeze solid. Carbon dioxide, for example, is a solid block. Even nitrogen and oxygen, the main components of our air, would condense or freeze if the conditions were right. Metals and alloys shrink, their mechanical properties change. Plastics and rubbers go from flexible to brittle. Lubricants that keep moving parts from grinding themselves to death can thicken or stop flowing altogether. Electrical cables and connectors designed for a certain temperature range experience stress as materials contract at different rates. If you're running a spacecraft or a lander here, every moving component, every hinge, every motor, every seal has to be chosen and tested for extreme cold. The chemistry you rely on, from battery reactions to propellant behavior, becomes difficult and sometimes unpredictable. Now think about shadows in a place like that. On Earth, going into shade cools you, but it's usually manageable. Around Saturn, in that dim environment, shadows are dangerous. A spacecraft in orbit that moves into Saturn's shadow can see its energy input from the sun drop almost to zero in an instant. If you're using solar panels, your power drops with it. The vehicle begins to radiate its stored heat into space, and without replacement from sunlight, it gets colder and colder. The source is not surface ice melting in sunlight. The material is coming from below, from a subsurface ocean that lies under an ice shell. The water is vented through long, warm fractures near the South Pole, called tiger stripes because of how they look in infrared and in imaging. Between those fractures, the region is hotter than you would expect for a frozen moon that far from the sun. That is your first clue that Enceladus is not just a frozen snowball, it is an active world with internal energy and liquid water. So once you know water is there, the next question is, does this ocean have the other ingredients you need for something like habitability? What would it take to call a place potentially habitable, even if you never see a single organism? When Cassini flew through the plumes and sampled the ice grains, the data showed more than just water. It picked up salts, like sodium compounds, and simple organic molecules, things built from carbon and hydrogen, sometimes with oxygen and nitrogen mixed in. The presence of salts tells you that the water has been in contact with rock, not just sitting isolated under ice. That is what you would expect if there are hydrothermal vents at the seafloor, hot water circulating through rock, dissolving minerals, and coming back into the ocean. For habitability, that combination matters a lot. You have liquid water as a solvent, you have energy in the form of heat and chemical gradients at those vents, you have chemistry with minerals and organics mixing. On Earth, deep-sea hydrothermal vents support rich ecosystems, even without sunlight, using chemistry as the energy source. Enceladus is not Earth, and this does not prove life exists there, but it checks the basic boxes: water, energy, and complex molecules. And all of that is happening on a tiny moon parked in a system that, overall, is incredibly hostile. So the twist is clear. You might have a cradle for life inside a radiation-blasted death trap. That is where the ethical problem starts for any future mission. How do you explore a place that might have its own biology without accidentally wiping it out with your own microbes? Every spacecraft we send carries some number of Earth organisms, even after cleaning. If you land something on Enceladus and that lander eventually breaks down and leaks, those microbes could get into the ice and, over time, reach the ocean. If Earth life can survive and adapt, it might outcompete or overwrite any native ecosystem before we even know it was there. So any mission that goes near Enceladus has to be sterilized to a level beyond what we normally do. You need strict planetary protection, careful assembly in clean rooms, heat sterilization or other strong methods, and very conservative choices about where you land and what you do with the hardware once the mission ends. The horror here is not just physical. Saturn does not only threaten you with storms, rings, and gravity, it confronts you with the idea that you could destroy an alien biosphere with one bad decision. The fear is not, can we survive there? It is, can we visit without becoming the threat? The good news, scientifically, is that Enceladus offers a way to study its ocean without drilling through kilometers of ice. The plumes themselves are samples of that ocean, sprayed into space. If you fly a spacecraft through them at a few kilometers per second, you can scoop up ice grains and vapor and run them through instruments, mass spectrometers, dust analyzers, maybe even devices tuned to detect specific patterns in complex molecules. You do not have to land, you just have to fly the right path with the right shielding and sensors. The stakes are huge. A single spectrum from those collected grains could show not just basic organics, but more complex ones like amino acids, or particular ratios of isotopes that hint at biological processes. You could get a fingerprint of ocean chemistry, maybe even a hint of life without ever touching the surface. The catch is that you still have to operate in Saturn's magnetosphere, in its gravity field, and in a region full of tiny particles moving at high speed. The mission profile is risky, and the science return is enormous, which is why Enceladus stays near the top of every list for future exploration targets. All of this leads to a bigger, uncomfortable pattern. Saturn's system hides its most promising habitable pockets in places that are not protected at all. Enceladus's ocean is covered by ice, but the plumes spray it directly into space, exposed to radiation, vacuum, and contamination risk. Titan's thick air shields its surface, but the chemistry there is so alien that anything we send is both a probe and a potential pollutant. These are not cozy, sealed biospheres. They are fragile niches sitting in a minefield of radiation, tidal forces, and human interference. So Saturn is not just a system of physical hazards. It's also a test of whether we can handle the responsibility of exploring places that might host life without breaking what we're trying to understand. And that leads directly into the next layer of threat, because even before you worry about oceans and microbes, you have to deal with the basic environment far from the sun, where light is weak, temperatures are brutal, and darkness turns every other danger up a notch. So the next question is, what does day and night really mean in a place where sunlight is only a faint glow and shadows can be as dangerous as any storm? How bright is day when you're 9.5 times farther from the sun than Earth is? At Saturn's distance, about 9.5 astronomical units, the sunlight is spread over a much larger area. The intensity drops to roughly 1/90th of what you get at Earth. So even when the sun is high in the sky, noon at Saturn is more like a deep, permanent twilight on a cloudy winter day on Earth. The sun is a small, sharp star, not a blazing disk. For you and your equipment, that low light level sets the tone for everything. Cameras need longer exposures, solar panels get much less power, and your eyes would never see anything close to a bright blue sky. The whole system lives in a dim, cold version of daylight. That sounds calm, but it's a constant reminder that you're right at the edge of where the sun still has much influence. And if the light is that weak, the next question is, what does that do to temperatures, and how does that affect chemistry and hardware? Look at the typical temperatures near Saturn's cloud tops. They sit somewhere between about minus 189 degrees Celsius to about minus 139 degrees Celsius, which is about minus 308 to minus 218 degrees Fahrenheit. At those temperatures, many gases you're used to on Earth would freeze solid. Carbon dioxide, for example, is a solid block. Even nitrogen and oxygen, the main components of our air, would condense or freeze if the conditions were right. Metals and alloys shrink, their mechanical properties change. Plastics and rubbers go from flexible to brittle. Lubricants that keep moving parts from grinding themselves to death can thicken or stop flowing altogether. Electrical cables and connectors, designed for a certain temperature range, experience stress as materials contract at different rates. If you're running a spacecraft or a lander here, every moving component, every hinge, every motor, every seal has to be chosen and tested for extreme cold. The chemistry you rely on, from battery reactions to propellant behavior, becomes difficult and sometimes unpredictable. Now think about shadows in a place like that. On Earth, going into shade cools you, but it's usually manageable. Around Saturn, in that dim environment, shadows are dangerous. A spacecraft in orbit that moves into Saturn's shadow can see its energy input from the sun drop almost to zero in an instant. If you're using solar panels, your power drops with it. The vehicle begins to radiate its stored heat into space, and without replacement from sunlight, it gets colder and colder. Then, when you come back into sunlight, you get a rapid reheating. Over a single orbit, hardware can experience huge temperature swings. Even with radioisotope generators, RTGs, providing steady internal heat, the outer structure, instruments, and appendages feel those swings. Thermal stresses build up as parts expand and contract. Solder joints can crack, materials can fatigue, and any mistake in thermal design shows up quickly. To compensate, you either run nuclear power sources or build solar arrays that are huge, on the scale of sports fields, just to get modest power levels. Either way, you are right up against the edge of what engineering can handle, just to keep the lights on and the instruments working. Distance does something else too, something psychological that is hard to ignore if humans are involved. The speed of light is fixed. At Saturn's distance, a radio signal takes over an hour to go one way. Round trip, a message from Earth to Saturn and back takes almost 80 minutes. That means if something breaks on a spacecraft, by the time the fault shows up in mission control, the event already happened more than an hour ago. By the time engineers diagnose it and send the command, it will be another 40 minutes before the spacecraft even hears the fix. There is no real-time joystick control. Every maneuver has to be scripted in advance. Every emergency procedure has to be built into the onboard software, because Earth cannot help you on the spot. For a human crew, that delay is brutal. You know that if something goes wrong, all the smart people back home will not even know for over an hour, and any advice they send will always be late. Saturn is not just physically cold, it's emotionally cold. It guarantees that help is always far away in both space and time. All of this, the dim light, the deep cold, the lethal shadows, the long communication delays, multiplies the risk from every other threat you have already seen. Storms are harder to track and predict when your sensors are power limited. Ring particles are harder to see and avoid in low light. The magnetosphere is harder to monitor when instrument lifetimes are cut by harsh conditions. Operations on Titan or Enceladus are harder to support when every update takes well over an hour to arrive. When the sun is this weak and this far, every failure is harder to detect and harder to fix. You have fewer watts, slower feedback, more thermal stress, and more isolation. That's the background environment Saturn gives you before you even start dealing with what's happening inside the planet itself. Because while the outside is dark and cold, the inside is the exact opposite, a place where temperatures and pressures climb to levels that rival stars, and hydrogen stops behaving like a normal gas at all. So the next question is, if the edge of Saturn's system is this unforgiving, what does the deep interior look like, where gravity has squeezed hydrogen into a metallic ocean, helium is falling as rain, and the core is hotter than the surface of the sun? How does a planet that looks soft and hazy from the outside hide a heart heavier than 10 Earths on the inside? When you strip Saturn down in your mind, the models say there's a central region, a core, with a mass somewhere between 10 and 20 times Earth's mass, squeezed into a ball about 20,000 kilometers across, around 12,400 miles. That core is probably a mixture of rock and ice, but not in any form you'd recognize. At the pressures and temperatures that deep down, rock doesn't behave like a hard solid. It behaves more like a weird, ultra-dense fluid. Atoms crush so close together that the usual difference between solid and liquid starts to blur. You're not looking at a calm, solid sphere sitting quietly under layers of gas. You're looking at material that's constantly under stress, constantly being squeezed by everything above it, constantly moving in slow, heavy flows. The weight of the entire planet is pressing down, and that pushes the physics into regimes we only probe for fractions of a second in the lab, with lasers and shockwaves. So the obvious next question is, if the core is that extreme, what's happening in the layers just above it, where the most common element in the universe, hydrogen, stops acting like a gas at all? Above the core, there's a thick shell where hydrogen is squeezed so hard that it becomes metallic hydrogen. In normal conditions, hydrogen is a light gas. Here, the pressure is measured in millions of times Earth's surface pressure, and electrons are no longer bound to individual atoms. They can move freely, like in a metal. The entire layer acts as a conducting fluid, a global ocean of metallic hydrogen, probably mixed with helium and other elements. This metallic ocean is where Saturn's magnetic field is generated. As the planet spins and as hot material rises and cooler material sinks, that conducting fluid moves in complex patterns. Moving electric charges create magnetic fields, and in a rotating body, those flows can organize into a dynamo, a self-sustaining magnetic engine. So when you see Saturn's magnetosphere carving out a giant bubble in the solar wind, you're seeing the result of deep, invisible motion in an ocean of hydrogen that used to be simple gas before gravity got a hold of it. And once you accept that hydrogen can become a metal down there, you have to ask, what is helium doing in that environment? And does it just sit there quietly mixed in? It doesn't. At certain combinations of pressure and temperature, helium stops mixing nicely with metallic hydrogen. It becomes immiscible, which basically means it prefers to separate out. Helium atoms clump together into droplets inside that metallic ocean. Those droplets are denser than the fluid around them, so they start to fall deeper toward the core. That process is often called helium rain. As those helium droplets fall, they lose gravitational potential energy, and that energy doesn't vanish. It turns into heat. That extra heat leaks outward and adds to the energy budget of the planet. Saturn, in fact, radiates about 2.5 times as much energy as it receives from the sun. It's shining in infrared because of this internal power source, not because sunlight is bouncing off and warming it up. Helium rain is one of the main ways Saturn turns its internal structure into heat, a kind of alien weather system that runs entirely inside the planet, invisible from the outside except through its effect on Saturn's overall energy output. Keep falling in your mind, and the numbers for temperature just keep climbing. Near Saturn's core, the temperature is estimated to reach around 11,700 degrees Celsius, more than 21,000 degrees Fahrenheit. That's hotter than the visible surface of the sun, which is only about 5,500 degrees Celsius. The farther you go from the sun's light into Saturn, the hotter it gets, until you are in a furnace powered purely by gravity and chemistry. This is a complete inversion of your everyday experience. On Earth, going into shade or underground tends to cool you down. On Saturn, going underground by falling deeper into the planet just keeps turning the temperature dial up and up and up. Pressure squeezes matter into new forms. Helium separates and falls. Hydrogen conducts electricity, and all of that releases and redistributes heat. There is no sunlight to blame for these numbers, only the raw fact that Saturn is massive enough to crush its own interior into a high-energy state. So, with metallic hydrogen oceans, helium rain, and a hot, heavy core, it's natural to ask the next question: how close is Saturn to being a star? The honest answer is not that close in terms of mass, but surprisingly close in terms of behavior. To ignite sustained nuclear fusion in its core, even at the lowest threshold for a brown dwarf, you'd need roughly about 3 times Saturn's mass. Actually, more. Saturn is nowhere near that. Its mass is only a fraction of what's needed. There's simply not enough weight to compress the core to the temperatures and pressures required to start fusing hydrogen into helium the way stars do. But the structure, the way hydrogen is metallic and moving, the way the interior is hot and convecting, the way the planet is radiating more energy than it gets from the sun, all of that looks like a smothered star core. It's as if you have the early stages of star-like physics, but without the final ignition. Saturn sits in a kind of halfway state, doing much of the internal work a star does, but without the stabilizing effect of fusion burning at the center. There's no fusion pressure pushing back. Gravity is doing almost all the talking. That's the unsettling takeaway. You're orbiting something that, in a sense, behaves like a muted star, running a metallic hydrogen dynamo, helium weather, and extreme heat in the dark, without the clean, steady balance that a real star's fusion provides. It's a deep, hot engine that never got to light up, still compressing, still leaking energy into space, still shaping the entire Saturn system with its gravity and magnetism. And if the inside is that intense, that dense, and that energetic, it raises a very practical problem for you as an explorer. Once you fall into a gravity well tied to a core like that, how hard is it to climb back out? How much speed and how much fuel do you need just to escape from the top of those clouds and get back into deep space again? How do you explore a place where leaving is 3 times harder than escaping Earth in the first place? Right above Saturn's cloud tops, the escape velocity, the speed you need to never fall back, is around 35 to 36 kilometers per second, roughly 80,000 miles per hour. Modern rockets launching from Earth only need about 11.2 kilometers per second, around 25,000 miles per hour, to break free of Earth's gravity. That alone is a huge engineering challenge for us. Now, scale that up. To launch from Saturn's upper atmosphere and actually get away, you need more than 3 times that speed. Not 3 times the throttle setting, 3 times the final velocity. Because of how rocket physics works, that means a ridiculous increase in fuel, staging, and complexity. If you picture a Saturn launch vehicle, it isn't just a bigger Saturn V. It's a stack so extreme that it stops being practical long before you finish drawing it. That tells you something important. Saturn's gravity well is so deep that we use it to trap unmanned probes, not to host launch pads. That depth shows up not just in escape speed, but in every maneuver. Near Saturn, every change in orbit, every inclination adjustment, every dive and climb around the rings costs more delta V than doing the same move around Earth or Mars. If you want to drop a probe down close to the rings to get high-resolution data and then pull it back out to a higher, safer orbit, you pay a high fuel price. Think of Saturn as a city where every taxi ride costs 3 times as much as the same distance back home, and there are no gas stations. Your spacecraft has one tank. That tank was filled near Earth, and after launch, there is no refilling. Every burn, every course correction, every extra safety margin cuts into the reserve you need to get useful science done and still maintain control. A mission planner looks at Saturn and sees not just a target, but a constant tax on every decision. And gravitationally, you're not just dealing with Saturn and a simple ring. You're dealing with a swarm. Saturn has at least 146 named moons and hundreds of smaller moonlets embedded in or near the rings. Each one has its own gravity, its own orbit, and its own resonances with the others. The whole system is a complex network of pushes and pulls. For a spacecraft, that means the gravitational field is not something you can treat as one smooth, simple curve. Over time, tiny tugs from different moons can shift your orbit. Resonances can build up, nudging you into or out of certain paths. Long-term stability is not guaranteed just because your first orbit looked clean on paper. If you choose very safe, simple trajectories, you spend extra fuel to keep control and avoid close passes that could add unwanted energy. If you choose daring, efficient trajectories that thread between moons and dive through gaps in the rings, you reduce fuel costs but raise the odds that a small, unmodeled perturbation pushes you into a path you cannot easily correct. So the architecture of Saturn's orbital maze behaves like an orbital labyrinth. There are routes through it, but they are narrow, and the walls themselves are moving. That's already a lot of risk for robotic probes. Now ask the harder version. What does this mean if you talk about humans living there, not for hours or days, but for years? A human outpost anywhere in Saturn's system would be one of the hardest places to evacuate from. Start with fuel. Any crewed ship you send has to carry or manufacture enough propellant not only to get into orbit around Saturn or one of its moons, but also to leave again. Getting back out of that gravity well needs serious delta V, much more than climbing off the moon or Mars. Then add time. A transfer between Saturn and Earth takes years, depending on alignment and propulsion. There is no emergency flight on short notice. Layer on radiation from the magnetosphere. Layer on the thermal extremes and the low light conditions. If something goes badly wrong, you can't just load everyone onto a ship and boost them home the way we could in a near-Earth scenario. Even if the ship is ready and fueled, even if the window is right, you're still committing them to a multi-year return through deep space, with limited chance to repair anything major once they leave. That turns the idea of a Saturn base into something that feels less like a research station and more like a one-way colony, where return is technically possible, but practically rare. Once you're in Saturn's gravity well, the system starts to feel like a slow, elegant trap. The same gravity that shapes the rings and sculpts the moons is also constantly pulling on your ships, your fuel, your station. Every day you stay, you spend resources maintaining orbit, fighting radiation damage, managing temperature, and keeping hardware alive far from any support. Leaving is always possible on paper, but always expensive in practice. That's why when you step back and look at the full picture, Saturn is not just dangerous to visit in a physical sense. It is hard to leave at all. In story terms, it's the classic horror house structure. Getting in is the easy part. Fall down the gravity well, use it to capture your spacecraft, enjoy the free orbital energy. Getting back out with enough fuel, working systems, and healthy crew is the part that keeps mission designers awake, and all of this is before you factor in one more twist. We still don't fully understand Saturn itself. We're not sure how old the rings are, we don't know the exact rotation rate, we're still arguing about the core structure and the details of the hexagon's origin. So the next question is, how scary does Saturn become when you admit that, even after decades of data and multiple missions, some of the most basic facts about this planet are still open problems? How do you spend decades staring at the brightest ring system in the solar system and still not know when it actually formed? That's where we are with Saturn. For a long time, scientists argued over two extremes. One idea said the rings were primordial, born with the planet over 4 billion years ago. The other said they were young, less than 100 million years old, formed long before Saturn itself. You would think, with all the data from Cassini and ground-based telescopes, we'd have a clear answer by now. We don't. Recent measurements of ring mass and how dirty the ice is push things toward the younger side. The rings are more massive than we once thought, but the ice is also surprisingly clean. More than 99% pure water ice with only a thin coating of darker material. If the rings were billions of years old, they should have collected far more dust and rock from micrometeorites over time. The fact that they still look so bright and clean suggests they might be much younger, maybe formed within the last few 100 million years. So you're left with an uncomfortable gap. One of the biggest, most obvious structures in the solar system, something you can see with a backyard telescope, might have appeared long after the dinosaurs. Or it might be ancient, and we still cannot state the age with confidence. For all our precision, we are still arguing over a difference of billions of years versus under 100 million, which is a huge range. That's the level of uncertainty we're dealing with on a feature that dominates the entire system visually. And if something as blatant as the rings has that kind of ambiguity, you have to ask, what else are we missing on more hidden properties, like the planet's own spin? You'd think how long is a day would be the easiest thing in the world to measure for a planet. For Saturn, it isn't. On a rocky planet like Earth, you can just watch surface features rotate under a telescope. On Jupiter, you can track visible cloud belts mixed with measurements of the magnetic field. Saturn is tougher. It has no solid surface to track, and its cloud features drift at different speeds depending on latitude and depth. Its magnetic field is also unusually symmetric, almost perfectly aligned with its rotation axis. That symmetry makes it harder to use the field as a clean clock. Different methods give slightly different answers for Saturn's rotation period, differing by several minutes. On human scales, that sounds minor, but for a whole planet, being unsure by even 5 or 10 minutes is a big deal. Imagine not knowing how long an Earth day is to better than that. You couldn't precisely track climate cycles, atmospheric dynamics, or interior oscillations. That's roughly where we are with Saturn. We know it spins in about 10.5 hours, but we can't pin down the exact number of minutes with the precision we'd like. That fuzziness gets even worse when you talk about the deep interior. We know there's a core region with more heavy elements than the outer layers. We know there's metallic hydrogen, but what is the actual structure? Is the core a compact solid ball? Is it more like a mushy extended region with heavy elements partially mixed into the surrounding layers? Gravity field data from Cassini, which measured how Saturn's pole changes as the spacecraft moved around, suggests the core might be more spread out than expected, maybe extending to 60% of the planet's radius. That picture is very different from the simple, small rocky ball plus thick gas envelope we used to teach. The more carefully we measure Saturn's gravity and how it wobbles and oscillates, the more complicated the internal structure looks. Instead of a sharp boundary between core and envelope, we might have a gradient zone where rock, ice, and metallic hydrogen blend. In other words, when we improve the measurements, the inside of Saturn gets fuzzier, not clearer. That's a problem when you're trying to understand how giant planets form and evolve. Then there's the hexagon. We can reproduce hexagon-like flows in rotating tanks on Earth. We know that if you have a jet stream wrapped around the rotating fluid and you tune the speeds just right, it can settle into a polygon pattern, often with 6 sides. That gives us a solid physical explanation for how a hexagon can form. But it doesn't fully explain why Saturn and only Saturn has a stable, long-lived polar hexagon in the solar system. Jupiter doesn't, Uranus and Neptune don't, Earth definitely doesn't. We also don't know exactly why Saturn's hexagon has persisted for decades without breaking down. The basic lab models don't capture all the real atmospheric complexity, like vertical structure, seasonal changes, and coupling to deeper flows. Even with supercomputer simulations and years of Cassini data, we're still tuning models, still trying to match the exact stability and shape of the real thing. The lab work tells us that the hexagon is not magic. The fact that Saturn actually runs one perfectly for so long is still not fully nailed down. Put these pieces together and you see a pattern. We don't know how old the rings really are. We don't know Saturn's rotation period to the precision we want. We don't know exactly what its core looks like. We don't fully understand why the hexagon forms and lasts only there. And this is not some distant exoplanet we've seen in a few pixels. This is the 6th planet from the Sun, visited by multiple spacecraft, observed by big telescopes for decades. That's where the real, quiet horror sits. Saturn is close enough to study in high detail. We can map its moons, dive probes through its atmosphere, measure its gravity and magnetism with precision instruments. And yet we are still guessing on basics: the age of the most obvious structure, the exact length of the day, the internal layout, the cause of a huge geometric storm. If we're this uncertain about a giant planet in our own solar system, one we directly visited with an orbiter for over a decade, how confident should we really feel about our models of planets we've only seen as dim dots of light around other stars? Saturn, by just being stubbornly mysterious, quietly undercuts our sense of control. It tells you that even when you throw your best tools at a nearby world, you may walk away with more questions than answers. And that brings up one last hard topic. If this system is this extreme and this poorly understood, is there any way anything can actually survive here? Whether it's microbes in hidden oceans or humans in metal habitats, without being crushed by physics, radiation, or our own mistakes. How do you talk about survival in a place where almost everything is trying to erase you, but a few tiny pockets might quietly keep going for billions of years anyway? Start with the smallest possible survivors. In theory, radiation-tolerant microbes could live on or inside some of Saturn's moons, especially Enceladus and maybe Titan. Down under kilometers of ice, shielded by rock and frozen crust, the radiation from Saturn's magnetosphere drops off. In Enceladus's ocean, or deep inside Titan's icy crust, microbes would barely see the storms, the rings, or the magnetosphere. Their main dangers wouldn't be Saturn's winds, they would be big hits and slow leaks, getting blasted into space by plumes or exposed by impacts that crack the ice. On Enceladus, anything living near hydrothermal vents at the seafloor would sit in a pretty stable environment compared to the chaos outside. Liquid water, a rock boundary, a constant energy source. The threat would be upward, being swept into currents that feed the tiger stripe fractures and then launched into space in the plumes. On Titan, possible life, if it exists, would be buried under atmosphere and ice, maybe crawling along in liquid water far below, or doing very slow chemistry in the methane seas near the surface. In both cases, the idea of survival is not about dodging storms. It's about hiding in the only places where Saturn's gravity and radiation can't easily reach, and hoping you never get dragged out of your shelter. But that's the microbial scale. What happens if you scale up and ask whether humans could ever live here not as brief visitors, but as residents? If you tried to set up human habitats around Saturn, you'd be building machines to cheat death on multiple fronts at once. The most realistic version is not a base on Saturn itself, but orbital habitats, big spinning cylinders or rings, parked in relatively safe orbits around the moon like Titan or out beyond the worst of the radiation belts. You'd use thick walls of water ice, meters to tens of meters thick, as shielding. Ice is great at blocking charged particles, so you mine the rings or local ice-rich moons, melt the material, and pack it around your living space as a protective shell. Inside, you'd keep Earth-like pressure, maybe 1 bar, normal air mix, artificial gravity from rotation. Outside, you're dealing with brutal cold, vacuum, and constant micrometeoroid hits. Your habitat has to maintain its orbit with regular station-keeping burns, because Saturn's gravity, plus tugs from all those moons, will slowly shift its path. You can't just park and forget. You're also smack in the middle of a system full of tiny bits of rock and ice, some from the rings, some from other sources, all moving at kilometers per second. Every one of those that hits your shielding is an erosion event. Every bigger fragment you miss is a potential disaster. Thermal management becomes a full-time engineering problem, radiating waste heat without letting the core freeze or overheat. Technically possible? Maybe. Easy? Not at all. You're maintaining a 1,000-ton life support shell in one of the harshest neighborhoods in the solar system. And then there's the biology you bring with you, which might be the scariest part of all, because moons like Enceladus and Titan are serious candidates for hosting native life. Any human presence in the Saturn system has to run under strict planetary protection rules. That means no casual crash landings, no uncontrolled hardware decaying out of orbit onto those surfaces, no sending dirty probes straight into potential habitats. Every lander going near Enceladus's ice or Titan seas has to be sterilized as aggressively as we know how. High temperatures, harsh chemicals, or other serious cleaning steps. If you want to bring samples back from an Enceladus plume or Titan surface, the chain of custody gets even more intense. You need sealed containers, fail-safe reentry systems, and controlled labs on Earth to make sure whatever you collected doesn't contaminate our biosphere either. In a setting like this, the monster is not Saturn, not the rings, not the storms. It's your own microbes, the bacteria and spores you carry by default, and the risk that they overwrite an alien ecosystem that never had a chance to defend itself. You're not just building habitats, you're writing biohazard protocols in a place where a single failure can change another world forever. Even if you solve the physics and the sterilization, there's one more layer that's easy to underestimate: the psychological hit. Picture life in a rotating ice-walled cylinder, years from Earth, with a dark striped planet filling half your sky. Communication delays are more than an hour round trip. If something fails, help from Earth is advice, not action, and that advice is always late. Outside your walls, there is no solid ground, only vacuum, radiation, and the knowledge that the giant below you has no surface to land on and no easy route home. Compare that to Antarctica or Mars. Those are extreme, but you can still say down there is rock, and we can send a rescue in principle. Around Saturn, every evacuation plan needs massive amounts of fuel, perfect timing, and years of transit time. One serious systems failure, one leadership meltdown, one loss of trust in the technology, and the psychological strain spikes. Isolation, distance, constant low-level fear of the environment, all of that stacks up. Even if we can engineer a survivable habitat, Saturn's system might still be psychologically unsurvivable for most people over long periods. That's why Saturn becomes a test of what habitable really means. It's not enough to ask, can you breathe the air, because you can't anywhere here. It's not even enough to ask, can you stand on the surface, because Saturn itself has no surface to stand on. The real question becomes, can your civilization build and maintain 1,000-ton shields against radiation, gravity, and cold, and keep them working for decades or centuries without slipping up? For microbes buried under ice, habitable might mean a stable pocket of liquid water, a small energy source, and a rock boundary. For humans, habitable in the Saturn system means turning raw ice and metal into a permanent self-sustaining fortress in orbit, with strict biohazard controls and zero room for error. Saturn forces you to admit that the classic Goldilocks zone picture is far too simple. You can get pockets of life in a system that as a whole looks lethal, and you can get technically survivable habitats in a place that would crush most people mentally long before the hardware fails. And once you've seen all of that, it sets up the final comparison, because Saturn is not the only giant out there. Jupiter is bigger, meaner in some obvious ways, and gets most of the scariest planet votes by default. So the last question you have to face is, when you stack everything up, the rings, the hexagon, the trapped oceans, the gravity well, the ethics, and the unknowns, why does Saturn, not Jupiter, end up looking like the real nightmare of the solar system? Who gets the title of scariest planet? The obvious heavyweight Jupiter or the quieter, stranger Saturn? Most people go straight for Jupiter. Bigger mass, stronger gravity, brutal radiation belts that would tear through a human in minutes. It absolutely earns its monster reputation. And you should concede that if you only look at raw power, Jupiter wins. But that's the trick. Jupiter is brute force. Saturn is something else. Saturn is subtle horror. It's death by geometry, by long timescales, by ethical traps, and by physics that feels wrong in ways your brain doesn't like. Jupiter shouts, Saturn whispers. And what it's whispering is, you don't actually understand planets as well as you think you do. Start with the rings. Both Jupiter and Saturn have ring systems, technically, but Jupiter's rings are faint dust bands, hard to see, thin veils of debris. Saturn's rings are bright, massive-looking, and active. They reach out almost 300,000 kilometers, nearly 180,000 miles from the planet, and yet they're only maybe 10 to 30 meters thick, a few tens of feet. They're made mostly of pure water ice, and they're not just sitting there, they're dying. Ring rain is constantly pulling charged ice particles down along magnetic field lines into Saturn's atmosphere, hundreds to thousands of kilograms per second. That means the rings are slowly collapsing, feeding the planet. They are a visible reminder that Saturn doesn't just hold on to things. It tears moons apart inside the Roche limit, spreads the remains into a razor-thin disk, and then, over tens of millions of years, eats that disk grain by grain. Jupiter's rings tell you dust exists. Saturn's rings tell you that gravity can execute worlds and then clean up the crime scene. Then there's the hexagon. Jupiter has its great red spot, an enormous, long-lived storm that's impressive and terrifying in a straightforward way. But its shape is still basically what you expect, a big oval, swirling chaos. Saturn, at its north pole, runs a storm that has decided to become a geometry problem, a clean six-sided polygon about 30,000 kilometers across, with each side around 14,500 kilometers long. No other planet in the solar system has anything like that. Not Jupiter, not Uranus, not Neptune. Only Saturn has a polar hexagon that's stable for decades, probably longer. You can make something similar in a lab with rotating fluids, which means the physics is real and repeatable, but seeing it appear naturally at planetary scale is different. Jupiter gives you big storms. Saturn gives you a storm that looks designed, and then forces you to accept that it isn't.
Now look at the moons. Jupiter's major moons are intense. Io's lava, Europa's ocean, Ganymede's magnetic field. They're dramatic, but Saturn's two standouts, Titan and Enceladus, hit a different nerve. Titan gives you an atmosphere thicker than Earth's, about 1.5 bar at the surface, mostly nitrogen with methane and hydrocarbons. It has lakes and seas, but they're filled with liquid methane and ethane at around minus 179 degrees Celsius, roughly minus 290 Fahrenheit. It runs a full methane weather cycle, with rain, rivers, and seas, on top of solid water ice that behaves like rock. From orbit, Titan looks Earthish, hazy atmosphere, smooth limb, large seas near the poles. Up close, everything is wrong. The air is unbreathable, the liquids are cryogenic and flammable, and any possible life would be slow and alien. It's familiar enough to trick you, but different enough to kill you fast if you treat it casually. Enceladus is tiny, only about 500 kilometers across, but it vents an actual subsurface ocean into space through plumes at its south pole. Cassini flew through those plumes and found water, salts, and organics, the same ingredients you look for when you talk about habitable environments. There's strong evidence for hydrothermal vents at the seafloor, a serious candidate for hosting microbial life. But that potential biosphere is parked right inside Saturn's radiation-soaked, gravity-dominated minefield. And that creates a very specific kind of horror Jupiter doesn't lean on as hard, the ethical one. Around Saturn, the risk is not only that the planet kills you, it's that you kill whatever might already be living there. Any mission to Enceladus or Titan has to be sterilized to an extreme level. Any sample return has to be handled like a biohazard. Saturn forces you to think about planetary protection not as a box to tick, but as a moral line. The scariest thing in the system might be your own microbes, not the storms or the gravity. So when you pull all this together and ask which planet is truly the most unsettling, look at the list Saturn stacks up. First, it's a planet that floats on water. Its average density is lower than liquid water, but it still crushes anything that tries to go inside it, with pressures of hundreds to thousands of times Earth's surface pressure, and temperatures hotter than the surface of the sun near the core. Second, it runs winds near the equator at around 1,800 kilometers per hour, about 1,100 miles per hour, and locks a continent-sized hurricane over its pole for decades. That's on top of planet-wrapping storms, the Great White Spots, that leave scars in the atmosphere for years to decades. Third, it has that polar hexagon, a clean, six-sided shape drawn in gas that looks engineered but comes from nothing more than fluid dynamics on a massive, fast-spinning planet. No other world does this. Fourth, it wears rings that are probably young, actively maintained by destruction and collisions, and actively dying through ring rain. Those rings are not decoration. They're a mass grave of shattered moons being slowly funneled into the planet. And finally, it surrounds all of this with a magnetosphere, a swarm of moons, subsurface oceans, and deep unknowns that combine physical danger, ethical risk, and psychological stress. It gives you possible life you might accidentally destroy, habitats that can only exist under meters of ice or meters of shielding, a gravity well that is hard to escape, and major questions about basic things like the age of the rings and the exact length of a Saturn day that we still haven't fully answered. So, if Jupiter is the solar system's muscle, the obvious bruiser with huge radiation belts and crushing gravity, Saturn is its nightmare architect, the one quietly running execution rings, geometric storms, venting oceans, and subtle traps in both physics and ethics. And that's why when you actually look at the data and everything it implies, Saturn is the scariest planet we've ever found.
This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.